Well, there are just two formulas that we'll use in this chapter. The first is the standard error, also known as the standard deviation of that distribution of sample means. And the expression is simple. It's sigma with a subscript m, and the equation is simply sigma, which is the standard deviation from the population, divided by the square root of the sample size. Piece of cake. What we're going to do in this chapter is actually assign probabilities to obtaining sample means with a certain value. And that probability will change as a function of the sample size. So here's that z-score. You'll notice it's slightly different. Instead of x minus mu, it's capital M minus mu. And instead of the standard deviation on the denominator, it's the standard error. We'll get into a few problems and that'll become clear. But before I go there, I want to draw something to make something clear here. This is, and let me stretch this just a tick. I gotta come up there. That's better. I hope you can see that. Back up. This is the distribution of sample means for an N of 4. And although I'm disinclined to do this, I'm using IQ scores here. The mean is 100. The standard deviation is 15. And what I've drawn for you here is all possible samples, and I shouldn't say all possible, but 4 possible samples of 1,000,000 that we could draw of size 4. So let's take all the purple ones. You can see by chance I had 4 members of the purple population, those purple X's, that all happened to be below average, and they left a mean that was below average. And conversely, I had 4 members of the red population that were above average, and they left a mean that was above average. And then look at the green X's. These are members of the individual population. The green ones were spread out. I had 2 that were below average and 2 that were above, and they left a mean that was smack in the middle. And then with the oranges, that was even more the case. They were really spread out, as you can see, and they left a mean that was smack in the middle. Here's the thing with samples of only 4 is that I could get aberrant samples. What do we mean by aberrant? A-B-E-R-R-A-N-T. Means unusual. Someone that's 7'6" is an aberration. Someone that's 2'6" is an aberration. Something unusual, away from the mainstream. When I'm drawing samples of only 4, could they all wind up below average or all wind up above? Of course they could. With only 4, we could get some aberrations. They could be aberrant. So, as we might suspect, the sway or the spread of the distribution of sample means is going to be somewhat broad with samples of only 4. You know, they can be fairly spread out. I could get some high means and some low means. But if you would, can I entertain a different proposition? Let's take samples of 144. Now, I haven't drawn that many X's up there for each color because it was going to drive me crazy. But imagine if I had 144 purple X's there, which I tried to draw. I spread those X's all over the place. Now, with 144, is it very likely that all 144 would be above average or that all 144 would be below average? Well, of course not. Isn't it likely with 144 that they'd be spread out all over the universe? Of course they would. And when they're spread out all over the universe, it puts the mean smack in the middle. Same with orange. Look at all the orange X's there. There's 144 of them. There are 144. Some high, some low, some middle, and it puts the mean smack in the middle. Same with green. So the notion is that when I have a high N, the distribution of sample means is likely to be narrow. It's likely to be tall and skinny. And if you'll focus on this just for a second, look how I drew it. In this blue distribution of sample means, for N of 4, I drew it broadly. It's supposed to represent that the means could fall all over the place. For this distribution of an N of 144, I drew it very narrowly. The suggestion being if I draw 144 people or evergreen trees or whatever the heck it is, in this case it's IQ scores, wouldn't it be the case that they're likely to be somewhat spread out? I'm going to get some highs, some lows, some middles. And therefore, that's going to land the mean smack in the middle. And sure enough, you can tell the blue curve, which is kind of faint. and all that spaghetti is skinny. It's almost like the thing that comes out of the floor of a cave, a stalagmite. It's tall and skinny and narrow if I have a large sample size. Now, would it be the case that the math bears this out, that this would be a low standard error or a low spread, a low standard deviation of the distribution of sample means? Yes, it would. If I have 144 and the distribution of sample means is very skinny, well, in that case, the standard error is going to be low. Conversely, over here, it's going to be a lot higher, suggesting that the spread of the distribution of sample means with an N of only 4 is a lot broader.